response, a dynamic excitation, a dynamic response, is it sufficient for me to go for a static design, or I have to go for dynamic design?
Dynamic design.
Dynamic analysis and design, you mean, right?
Yeah.
Yes. So when you do your chapter with Prof. Azlan, what analysis that he covered? What analysis design that he covered? Is it static or dynamic?
Dynamic.
Dynamic. Are you sure? You cover the force method, right?
Yeah.
Then what you did is that you have this building, and then you calculate how much is the base shear, and from this base shear, and then you distribute it to this level. Is it?
Yeah.
And this base shear you calculate based on the equation that you get from the code. Is it correct or not?
Yeah. True.
Yes. So is this static design or dynamic design?
Static.
Static. So just now you said dynamic. You take back your word. Now, all right. So as your friend said, if I have one base shear and then I distribute this to the level, it's this base shear. I use one value, right? It doesn't. You don't see any T domain over here. Correct or not?
Yeah.
Yes. So can I say this is static or dynamic? So it's a static, right? That's why I said before we go through our design, before we go through further in our class, I really need you to understand the difference between the static and the dynamic. Why is it like we say dynamic load, static load? This way you don't interchange with the others. Now let us see first what you have done with the earthquake and what you're going to do with wind as well in this class. Now, when you come to earthquake chapter with Prof. Azlan, what you did is that you calculate your base shear. And from this base shear that you calculate based on the equation from your code, and you distribute it to the height of your structure as the horizontal load. And this horizontal load, you don't see any time domain over here. So this is static because it doesn't change with time. It is similar to this one. Vertical load doesn't change with time, but right now in here, horizontal load doesn't change with time. It is static. It is static analysis or static design. But the load that you consider in here is from the earthquake load, which also change with time, that you can represent it into the base shear, that you can also go for the static load. All right, so these two you have to understand first whether it is static or dynamic. Now, why? My next question is that why we do static or dynamic design, whether it is safe or not, whether it is acceptable or not, because you say here it is earthquake, and for what your friend said, dynamic excitation got dynamic response, and that's why you should go for dynamic design. But what you did all this while, it is the static analysis or the static design for your earthquake, right? So the question that you should ask yourself, whether this is acceptable or not, whether this is like safe or not, and if your answer is yes, when you should consider it to be static, whether it is for all design that you are able to consider it to be static, or there are structure that you need to consider it as dynamic, right? Because definitely it's not going to be as simple as like everything you can do for a static. Then definitely also, if I am your consultant company owner, then I said, okay, I need you to design this building like I'm going to construct a school, and this school is going to be 4 stories level. So it's going to be constructed in, for example, in Johor Bahru. I need you to propose to me what kind of analysis that we are going to do, whether it is okay or not. And he may add like, okay, I heard that this seismic design is in right now, or wind design is in right now, so I need you to do it too. And do whatever you want, can with this fancy computer simulation or whatever. So as a design engineer, your first task is to decide what type of analysis that you're going to do and whether it is safe for your structure, whether it is acceptable for your structure or not. So this is where we are, the terms that you need to understand, right? Now, when we wanted to decide whether what kind of structure or what kind of analysis is suitable for your structure, is that you need to check not only your structure itself, but also the loading or the excitation that is imposed to your structure. Like your friend said, the excitation that comes from the loading and also the response that comes from your structure. So when it comes to wind and earthquake, these two has to be considered simultaneously. You cannot only look into your excitation, no, or you cannot only look at your response, no, you have to look into both. Now, how we decide whether we should go for a static, okay, like you did during the earthquake class, or you should go for dynamic analysis, which is more complicated and you have to do using the software and everything. Okay, so this is the first stage. You need to decide first. You have to go for a static or you have to go for a dynamic. And for this one, you need to consider both excitation and response. So if I can draw it a little bit in here for you to understand it, right? Okay, so if your structure and this is from your excitations. So this is from your, for example, your building, okay? Or your, okay, because we are considering these two depends on the number of that. For example, we said the natural period of the structure equal to n over 10. Okay, my building, say I have 4 levels. So you know that the structure in natural period is going to be 0.4 second. Now for earthquake, the natural period of n over 10, so 40 divided by 10 is going to be 4 seconds. Now, let us see the condition if this building is constructed in Sabah, and also this one, where you have a local earthquake, or when it is imposed with wind, right? So we knew that the natural period of the structure is 4 seconds for the high rise and 0.4 second for the low rise, and also for earthquake. Let's take 0.1 and 0.4 second as the natural period. The one that we have in Sabah before this, it is around 0.35 seconds. So we make it 0.4 second for simplicity, and for wind we take 4 seconds. Okay, so what this beta is given, it is the ratio between the natural period of your structure and your excitation. So it is like this, right? So beta factor is Tn over T prime. Now if I have my structure, the first one, okay, the short building, and this short building I impose with the first I impose with the earthquake. Okay, so this one is earthquake excitation, and I say this is the wind, and this is my structure. This is the n equal to 4. So for this beta, it is Tn over T prime. So this one is my Tn equal to 0.4 second, and my earthquake is 0.4 second, and my wind is 4 seconds. So my beta here is going to be 0.4 second from my structure divided by my earthquake 0.4 second. So I have beta factor equal to 1.0. And now if for the same building, if I impose with wind load, I will have the beta ratio equal to 0.4 divided by 4. That will give me 0.1 second. Okay, so keep this value first until we come to the discussion after that. Now if I have the long structure, which is n equal to n equal to 40 and the natural period equal to 4 seconds. So if this high-rise building I impose with a local earthquake, my beta ratio is going to be 4 divided by 0.4, and I will have 10, right? So if I impose with wind load, I will have 4 divided by 4, and I will have 1 ratio. Sorry, this is not second, this is the ratio. Okay, so what you can see about this is that what your beta ratio can give you, it's give you the amplification factor for the dynamic amplification factor. What it says here, okay, if I plot, this is my beta ratio, and this is my dynamic amplification factor that normally we allocate as TR, and this is 1. My curve is going to be something like this. And this is beta equal to 1.0, and this is 0. Okay, and this is dynamic amplification factor equal to 1. So what you can see here is that if my beta ratio is 1.0, the dynamic amplification factor for this curve is going to be the maximum, right? So in here, we said that if your beta factor is 1.0, you reach to a resonance effect. So meaning, if you have your displacement delta equal to, for example, 10 millimeter, but your dynamic amplification factor is 9, then you are not only looking at displacement of 10 millimeter, but times 9. Because this is the dynamic amplification factor. Whatever factor in here, it is going to be multiplied with your response of your structure. So if you have displacement 10, it is under the, if your beta ratio is equal to 1.0, it is no longer 10. You have to multiply with 9. And if it is like somewhere around here, beta equal to maybe 0.8 or something, then your amplification factor perhaps is 0.5, then your displacement is going to be 50 millimeter instead of 10 millimeter. What if your amplification factor is 1? So whatever you have, if you have 10, multiplied by 1 is going to be also 10. So meaning it is a static. It is similar with this, whatever static analysis give you, because it's going to be the same. The amplification factor is 1. So in here, in short, what you can see is that if, for example, I have this short period of building, n equal to 4 level, which one, under which condition is going to be giving me the highest amplification factor, that is beta equal to 1? It is under earthquake, right? Because in here, under earthquake, local earthquake, I will have equal to 1. But the same structure under wind is 0.1. So 0.1 is around over here. So my amplification factor is 1. So meaning it is under static. However, if I have a long period of structure, which is high-rise building, under local earthquake, my beta factor is 10. So I go somewhere around here. And how much is my amplification factor? Is around this side. Okay, so there is no response because it doesn't make any response to me. However, for my wind, it is 1.0, so I fall into here. So whatever I have is going to be multiplied a lot with my dynamic amplification factor. So I have to be careful, because if I design with static design and I have 10 displacement, actually it is not the real displacement. The real displacement will be multiplied with the amplification factor from dynamic. It may be 5, it may be 6, it may be, how much is it, depending on the building itself, because the amplification factor comes from my properties of my building. So in other words, if I'm designing my structure, you always hear that, okay, if you are designing high rise, you have to design for wind. So this is why it is, because when it comes to wind, the natural period of my wind is a longer period. So if my structure also have a longer period of natural period, it may fall into the resonance effect. However, for a shorter building, you may say that, okay, if I'm designing a 4-story of apartment or 4-story of a school, I don't need to design for wind. Yes, because why? The wind will give you almost no the amplification factor, and it is similar to static. So you can design, you can check on the wind effect, wind load using your code, because what code is given you is a static design. That's why just now your friend said, okay, Dennis told us that when you do it Propaslan, we teach you how to do the base shear force and then distribute with, to the level of your structure. That is a static design. You are doing it statically. You are looking at your earthquake load as a static load. It is acceptable for cases where the earthquake load is not governing. However, when you are designing a structure in which earthquake load can govern to your building, it is also advisable for you to look into the dynamic analysis of that earthquake load impact to your structure. Understand, right? So similarly, if you are designing for wind load, if you are designing for high-rise structure, you can use a static method or static design that is given to you by the code, but the code is not going to give you complete guarantee that your design is going to be safe. The code, each code has a limitation in terms of the height of the building that you can use the parameters and the procedures that is given in the code. For example, for the wind code, if you are doing with using Eurocode, it says that the height it is maximum of 200 meters. Beyond that, it is not it's not advisable for you to use the parameters and design procedures given in the code, because why? The dynamic effect of your structure may be governing, meaning your structure may give you a dynamic response for the wind loading that you are imposing to it. However, when it is less than that, say, okay, you can use it with your precaution. And for American code, it says that edge is not supposed to be more than 400 feet in order for you to use the procedures that is given to you. Okay, so that is why in your class, in your earthquake, it is okay for you to learn about the static method. And in this class, what we are going to teach you for wind design, we are going to teach you using the static analysis or the static design using the Eurocode and also the American code for comparison. Okay, but most of the examples, most of the design analysis, we are going to use Eurocode together with Malaysian National Annex. Now, I'm sure some of you are international students. There is not too much concern. You shouldn't concern too much like, okay, we are using National Annex, Malaysian National Annex, but I also have my local annex. It is whether it is acceptable or not. Yes, it is acceptable because this annex is only some part of the code which is referring to the national annex. So some part, the main part is still using the main code. Like in Malaysia, we are currently using the Eurocode. So you can also, and I believe that in many countries also they are using Eurocode. And if you're using other code, you can see that the procedures also are not too much difference, only the parameters, the notation, some values of the parameters might be different here and there, but the overall procedures, the overall factors are all similar, okay? Now, that is the thing. I need you to understand in this class what we are covering for you. We are not going to teach you dynamic analysis. No, even though you may say wind and earthquake are dynamic load. Yes, they are dynamic load, but they are not always imposing dynamic response to your structure, except for the structure when they are more governed by the wind or earthquake load, then they might have a dynamic response in which, for example, the easiest way for you to check on them, you can check on the beta ratio over here, okay? When they are far from it, then you can say that, all right, it is safe for me to go for a static design, static analysis first in order for me to proceed with my design. So this is what we are going to cover. For those of you who are doing your master project, your final year project for bachelor degree, then you may go for dynamic analysis because it takes a lot of time and a lot of effort. Okay, so we have already covered this, and the last one is about linear and nonlinear. All right, so a lot of talking from my side. Let us see who can help us with the linear and nonlinear. Muhammad Amiruddin, where are you?
Yes, Doctor.
So please explain, share with us your opinion on the linear and nonlinear analysis. Let me ask you, Amiruddin, the design that you do before this, maybe in your RC design that you think, is it linear analysis or non-linear analysis?
Linear.
Linear. Why do you think it is linear?
Because
did you use this E factor in your design, Amiruddin?
for earthquake design, I think I use the E value, but for the RCD, I don't use it.
You don't use it. So for earthquake, you use this E value, right?
Yes.
So do you understand what is this E value?
Young modulus.
Young modulus.
Is
What
it?
the Young modulus said to you about this? What do you learn? What do you understand about Young modulus?
Stress over strain.
Okay, stress over strain. If I have stress over strain, okay, So this is my stress, this is my strain. So this is the Young modulus. Yes? This is E. Is it?
Yes.
Yes. So what you can see about this, is it proportion, stress and strain? Yes or no? So for example, for this curve, if I make it like this, can I use E on here? On this point, can I use still E or not?
I
Amiruddin?
think no.
No, because it's not proportion anymore, right?
Yes.
Yes. So like Amiruddin said, when it comes to linear, during your design, you sometimes use this one, E, right? What does it mean? So in our design, first let us see linear and nonlinear. Linear and nonlinear is like if you, for example, if I have a road, okay, this is my road, and you know this tensile test in your lab. You have a road, and then you pull it in one side, and you pull it another side, and because of you pull it, your road become thinner, and then become a little bit longer, and then thinner and longer until it just break in the middle, right? And from here you get what is the area before the test, and what is the area over here after the test. And then you get what is your strain, and also you get what is the force divided by the area over here, you get the stress. So this is what you call then you plot the graph. So this is the graph that you plotted, and according to Amiruddin said that this is the Young modulus, in which between this point, if I pull this rod, I released it, it come back to the original position. I pull it, I release it again, it come back. I pull it, I release it, it come back. But when it passed to the yield point, if I pull it until this one and I release it, it will not come back to zero anymore. It will go like this. And then again, I pull it, and then I release, it follow this road. I pull, I release, it follow this road. And then until eventually it just fail. So from this point to here, we call that this is linear, because according to this modulus of elasticity that you can represent your material in here, whatever force that you give, the moment you release it, it is still go back to the original position because it is still proportionally linear. And after this yield point, if I impose more load, it cannot go back anymore, meaning some part of the properties is already yield, it's already damaged. Now, when I try to let you picture this in your like your structure over here, okay? If I have my horizontal load and I have my displacement, okay, and I plot this as displacement and loading, my horizontal load, okay? Now I increase my horizontal load, like for example, from 5, then I have displacement 1. I increase 10, displacement 2. I increase 15, displacement 3. And I plot it. Plot, plot, plot. I release this one, it come back, my structure. I release it, it come back, come back, come back. But if I give, for example, 35, and it reached to displacement of 8, for example, my column start to crack. My beams start to crack. So meaning yield happen on my column. I may come to this point. Now, if I release it, it never come back again. It is just like here. And if I put more load, it may just come back here, it goes here, and then it goes to this side. Okay, so if I plot this graph, it's going to be almost similar to this, right? Now, what it can say here, in this linear way, whatever imposed load will have proportion displacement, and if I release them, it go back. If I release them, go back. In other words, there is no yield happen. My beam, my column, my everything stays the same. This is what you did in your design of your RC Design 1, RC Design 2, in which your graph, you're looking at here, proportion. You give how much is the load, right, your moment, and you get, okay, this is going to be my design of my rebar and everything, because you design it in such a way that you think it's going to be linear proportion. There is no cracking and everything. That's why you always give your factor of safety. You are playing on this line. But in real world, it's not going to happen like this, especially if you have a horizontal load that is imposing to you. You may go for yielding and eventually fail. So when it's going to be happening is when you have your yield over here, because they cannot come back to the original position anymore. So this is when it says, and this part is linear analysis, and this one is non-linear. All right, so linear, non-linear. When you are looking at linear, you are expecting it to behave like this. One, you are expecting no damage, no yield, no nothing. They can back to the original position. That is linear. But when you are looking into analysis, that you want to see what happened if yield happen, like if I put load, how much load I can impose until this beam crack. What is the load that is still safe for me to give to my structure before this beam damage? If your intention is to look into this, linear analysis cannot give you the information that you want, because linear analysis stand on the concept that it follows this line. It doesn't have any cracks. So for this condition, it is non-linear analysis when there is already damage here and there. So in this class, you are not going to go for non-linear analysis. You're going for linear analysis, in which whatever design calculation that you have, you expect your line to be in this line over here, okay? So in short, in this earthquake and wind, when you graduate, you go outside there and you say that, yeah, I learned wind and earthquake design, I can do the analysis. So be careful and bear in mind that the load of what you consider in your analysis is the static. Wind and earthquake load is static load. Your design is also a linear design, and you expect your structure not to have a dynamic response, in which they are not governed by wind or earthquake load. If they are governed, then you have to check it with the dynamic analysis, in which you can do it with your some software, some calculation in terms of the dynamic amplification factor and things like that. Okay, so I hope you are clear what you're going to get from this class, what you already get from this class if you already have done your earthquake design and everything like that. Okay, and in which condition it is safe for you, and in which condition that you have to be giving a bit more precaution. So are we clear? Do you have any question? No question, class. So if we have no question, then we can continue with our introduction. Importance of structure design. Okay, this one we already covered by my explanation just now. You can just check on it. This is the graph that I showed to you, the beta factor. So this is the beta ratio, and this is the dynamic amplification, and this is the curve. This is plotted for a different value of damping ratio, and I'm sure also you have damping. You knew about damping ratio, right? When you do your structural dynamic, in which part of your structural dynamic calculation you use your damping ratio? Can anyone share with me, just to recall to refresh our memory? Haris, where are you, Haris? Haris, can we hear from Haris? Is Haris around? Or Haris tengah tidur? Ho Hui Min? Can we hear from Ho Hui Min? My question is that, yes, here you have this graph, the one that I showed to you is plotted for different damping ratio. You have damping ratio 0, 1/5, 1/4, and 1/3. So my question is that in which part of your dynamic calculation you have this damping?
I think it's at single degree of freedom. Single degree of freedom calculation.
Single degree of freedom you have. So multi-degree of freedom, you don't have damping. Yes? Who? Can we hear from Lee Yizwan? Lee Yizwan, can you also give some opinion about this damping?
Maybe a calculation for the response.
The coefficient for?
Calculate the response. We use the damping.
Calculation for the right force.
Yeah.
The damping.
Yeah.
Okay. What do you
Different
can
damping.
see? Huh?
Different damping ratio will cause different response.
Got different response for the damping.
Yeah.
Right. So thank you for your response, and let's call for another one before we discuss about this. Jevanaraj, where are you? Jevanaraj? So just now, Haris is not responding. Jevanaraj, I don't know whether they are here or not. That's okay. Let's check on them later. Lim Zeng Hong. Lim?
Yes, doctor.
Yes, Lim. So I want to ask you, what do you understand about damping?
This time resistance to against to the period.
Resistance towards the period.
Or no, I'm not sure how to describe.
Not sure how to describe. Okay, let us, if I can put it like a very simple word, okay? You know this game, right? There is like, it is on they normally install in the triangle like this. And then there is bubble, like there is the steel mass. It's very small. And if what they did is that they pull this one, and then this one goes here, and then it hit this thing, and then it start pushing it to the other side, and then this one also push to the other side, and then it goes like this. So if you can see my video right now, it is something like this, and then they pull, and then it doesn't stop. The moment I take this end one and then I hit the other one, and then the end one also goes here, and then it hit here, and then again it goes here, hit here, and it's always left and right, left and right, left and right, until I try to stop it and it stops. Do you know these things, that this like steel bubble that you put left and right, right? So now, for this thing, if I don't stop it, it doesn't stop. Or for better say, if I have like a pendulum here and I have a mass, and if I push it a little bit, it will start to move left, right, left, right, left, right, left, right. Now, this system, if there is no damping, in which we call it the C over here, okay? C. If there is no damping, this system is going to always moving left, right, left, right, left, right. But if I start to put some like stopper over here, like I put my hand to stop it, eventually it will stop little by little, stop, stop, stop little by little. So my hand or my finger here is acting like a damping. Damping means it damped the vibration. It comes from damping. It comes from damp. Or if you have a device that reduces the vibration, it's called damper. Because the job is to damp the vibration. Like your friend said, it reduced the vibration. So it damped the vibration. It is damper. When there is like a system, the damping, it will try to reduce the vibration. Now the damping, the job of this damping is that the damping factor, the damping ratio, we say, if your damping ratio is high, for example, you have 5%, okay? Eventually, this vibration is going to stop. But if I have damping ratio 10%, it is higher, right? From 5%, what's going to be? The vibration is going to reduce faster because I have more damping. Now, if I increase it to, for example, 20%, maybe after few vibration, it is already stopped. So this is the damping ratio. In your calculation of your dynamic calculation, you have this one, right? Okay, so this is the, and this is the mass, this is the acceleration, this is your damping, and this is your velocity, this is your stiffness, and this is your displacement. So this is where you consider damping in your calculation of your equation of motion, that is the C. So this damping, the job is to reduce the vibration. If your damping is 0, eventually it will reduce, but very, very slow, okay? So this is why this is the curve where the damping is 0. So it doesn't give you the value of it because it is infinite. That it's like unknown when it is going to stop. But if you have damping of 1/5, it is going to reduce your amplification factor to this much. And if I increase my damping to 1/4, which is 0.25, it's going to be until here. That is my amplification factor. And if I increase my damping to 1/3, my amplification factor with the same beta ratio 1 is going to be 1.5. So in other words, if you fall into the category of your beta ratio is having resonance, all right? Now, what you can do to reduce your amplification factor, your dynamic amplification factor, is to increase your damping. Okay, because if I increase my damping to 1/3, my amplification factor is around 1.5. But if I have 1/5, my amplification factor is 2.5. So whatever response I have, I'm going to multiply it with 2.5. And if I don't have damping in my system, I may go for this one. Okay, so this is how it is, in which in this graph, you can see that how damping ratio is going to save your structure, whether it is going to reduce the vibration or not. So some structure, like for example, high-rise building, after they have constructed, they feel that there are too much vibration on the structure. They are too like susceptible to wind, vibration and everything. This is the time when they add damper. So the damper added to a high-rise building is going to help the building to reduce the vibration that comes from the horizontal load. They may install like a mass damper, or they can install a liquid damper, or they may install like a viscoelastic damper. Or this type of damper is to increase the damping in such a way that you can reduce the vibration of your structure. So this is also another channel of research, another channel of topics that if you're interested, you may go into detail about it, okay? Now this is also we already covered. Okay, so in terms of the dynamic response that we have mentioned to you before, this is the one that I mentioned to you, the damping ratio matters. If you don't have damping or you have damping, then the dynamic response is going to change significantly. Or for example, the frequency of the excitation, the duration, and also the strength and ductility. Now, where is the strength and ductility matters over here? The ductility is from this curve, okay? So this is the curve that you have, the one that I showed to you, linear and nonlinear, and this is the linear part, the moment it yields, and it will have some going into the nonlinear behavior until it eventually fails. So what is ductility given to you? Ductility is the stage from the yield, the first yield, until the ultimate capacity of your structure. So the more in here, what is it? The more ductile your structure is, you have a prolonged curve. So meaning you have like your structure can retain some part of itself before it is eventually collapsed. So if you have a higher ductile structure, for example, in a building, you have a higher ductility structure, you can save your people from running out from the structure before they are completely trapped in the collapsed building. However, if the structure is like this, after yielding point directly collapse, then the time that you have in order for your people to save themselves is very short, meaning after few vibration, like after the structure, it is in a brittle behavior, the column may completely collapse before it yields like other part as well. So we do not want this behavior to happen. We want the higher ductility. So when you are looking into dynamic, you also look into the ductility of your structure. Now, vibration mode and associated period, I'm sure you already learned a lot about that. And for example, your friend just now mentioned a single degree of freedom, and also you have multi-degree of freedom structures. So if you have a single degree of freedom like this one, the vibration mode is going to be one mode. And for this thing, you have your period. How much is the time to get from this point to this point and then back? So that is one period. And if you have like the 2 degree of freedom, so this is the first mode, and the second mode can be like this one. So this is also the time, the period for the second mode of vibration. And you have 3 vibration mode. You also have 3 associated period, and this is also related to your mass. Okay, so this is the first one. Right, so these are the factors that you need to understand for when you are dealing with dynamic response, and the comparison between static and dynamic. Of course, in dynamic you have the mass, right? As I mentioned to you, you have mass. It is for this damping plus the stiffness, and also this is the so this one is the mass, damping, and also stiffness. Sorry, this one is all right like this. So this is the time for the dynamic response. You have mass, you have also damping, but for the static you do not have it. And you also need to see the relationship between supply and demand. What does it mean? Is that what your structure can give and what is the excitation need from your structure. For example, the supply, this is the capacity of your structure. Okay, with your design, you know how much is the structure can be strong for this one, and then the demand comes from the earthquake. How much is the demand from the earthquake? For example, if you have this type of earthquake, or you have the wind loading like this, how much is the demand? So this relationship is matters for the dynamic. But when you do your static response, no, you don't check on this one. You just check on, okay, how much is the W and how much is the capacity that I can give. Change in materials in dynamic response, yes, because in dynamic response you have this. Okay, the elastic the yield until it is eventually collapsed. But in static, no, you only have your elasticity modulus. Hysteresis also matters because in hysteresis loop, you know, like this one, and if I release it, go back. Then if I increase it go back again. So what does it give you in hysteresis loop? If you calculate the area of this, like in the area under your graph, it is going to give you how much is the total energy released from your structure. Okay, and definitely in static, you don't have this one. You only look into your dynamic response. Okay. So a little bit overview on your wind and earthquake excitation. For example, in here we have for wind, I mentioned to you it is for long period, and excitation is between 3 to 60 seconds. This is one gust. And it will have dynamic effect on the long period of structure like long rise building and then long span bridges in which their natural period is longer than 3 seconds. And also it will have static or like quasi-static for low rise and short span bridges in which we already discussed about this one. And another thing that is very essential for you to understand about wind effect on structure, it is the relationship between the height and the wind velocity. So always we have the wind velocity like this, and this is the height from 0, and this is the wind effect that is coming to there. So the higher you go, it's going to be even more prolonged. The risk, of course, there are going to be a structural failure, the cladding failure, the instability, and also serviceability problems. But however, thank God in Malaysia, we don't have a risk too much produced by wind, except for sometimes when there is a typhoon happening in the neighboring countries, like in Sabah or in Sabah coastal area. We have a risk of a typhoon that comes from the Philippines, in which you can also produce risk to our structure. Other than that, Alhamdulillah, we still have a good stability. And these are some examples that you can, of course, see a lot in the internet right now. That is the effect on the civil structures. And also another example from resonance is happening on the Tacoma Bridge. So if you Google it, and then you can see what happens when resonance happen on your structure. So for the Tacoma Bridge is that you can see the middle span having this displacement, and eventually the displacement become very high as resonance comes to the structure, and eventually it collapses. Okay, so you can check on this. Now, I mentioned to you when your structure is like the dynamic effect also govern on your structure. Other than doing your the dynamic analysis, it is also essential to go through a wind tunnel test. Now we have a wind tunnel lab in UTM, in the Aero Lab. What this wind tunnel is able to give you is that if you check on your code, it will give you pressure coefficient, right? So for example, if I'm going to design my structure, what code is given? Okay, it's giving me, well, what is the pressure coefficient on this level, on this level, on this level, on this level, and also if I have a roof, what is the pressure coefficient on here, what's the pressure coefficient on this roof. But if your structure is not safe to use this pressure coefficient given by the code, it is recommended for you to go through a wind tunnel. So wind tunnel, what it gives you, if you see in this picture over here, it is a long span bridge in which what they did is that they will place sensors on these cables, sensors on each part of this structure over here. So they will place this model in the wind tunnel facilities. Normally it looks like this one. You have a wind blowing like this, and there is a fan, and you will place your your sample in some part of this wind tunnel test. So some part over here, you place your samples, and from here, if you can see in here, the wind blow like this. They're first going to see if there is how was the pattern of the wind blow, whether there is a vortex excitation coming, and they're going to put some sensors in some part of the structure in order to get how much is the pressure that comes from the wind. And from there, they can go through some verification model in order to design the structure using the parameters that they get from the wind tunnel test. So for these procedures, not only it is taking time, but it is also very costly. Just to give you some idea, based on our project with to construct a bridge that is spanning from mainland into the island in Sabah. The bridge wasn't too much long. It is 1.3 kilometer, and our sample also is like very small. The area that we have in UTM is only 1 meter square, the area for your model. So it is, you can see that for 1 meter square, the sample is not too much big. It is very small. However, for this project, they charge us 80,000 ringgit for conducting the test, for giving the results. So you can see that 80,000 is not a small money. And if you have a project that you need to design, like a high-rise building, and then it doesn't fall into the safe condition for you to design with the code, and you have to go for a wind tunnel test or a CFD analysis, things like this, then that's why they don't go completely directly to a wind tunnel test, because one, it is costly. It is not like a small amount of money. So this is some kind of approximation. However, if you are designing, like for example, a big project in which like it is very essential for you to get the response of your structure in a real condition, not like the code given parameters, then you have to go for it, right? The wind tunnel also can give you like a modification on your design. For example, for a special structure, what they did is that they model the structure and also the building surrounding it in order to see how much is the effect of the wind if they construct it like this way, and how much they can reduce it if they change the design, some part of the design. So this is also very useful parameters that you can get from a wind tunnel like this one. And from there, they can make some strategy in order to reduce the wind excitation. For example, one is like a softened corners, tapering and setback, or you can varying cross-section shapes, spoilers, and also porosities and openings. So there are many methods right now that has been used in order to reduce wind effect on the structure. And all this kind of approach can also be checked on the wind tunnel test. So for example, the Taipei 101, what they did is that from the original design, they modified it with some modification on the corner, and eventually it reduced 25% of base moment using the new design. And these are all conducted using the wind tunnel test. Or the Burj Khalifa, setback, changing cross-section and orientation. So you can see here some of the building where the surrounding structure matters to the wind effect. They model it, and some they model as an open area. So Petronas Towers also, when we design it, we use the tapering effect. So what is the tapering effect? Is that we actually utilize buildings around the tower in order to reduce the wind effect on the twin tower itself. So when you go for your Eurocode, you will see that in Eurocode they have given you some parameters in order to include the effect of these buildings around your structure into your calculations. So later we will see about that, okay? The effect of the neighboring structure itself. Shanghai also, it has twisting and tapering. Now for this part, I'm going to give you your homework in which you're going to choose one structure, either a building or bridges that is critical to wind, and you can discuss some risk and prevention approach taken to reduce this effect. Okay, so try as much as you can to do it yourself, not using ChatGPT, although I know that most of you are going to eventually referring to ChatGPT, but it is also good for you to do some research on your own for this stuff. Okay, so we are going to have our first homework in which you're going to get me I think around 5 pages, not more than 5 pages. Okay, so it is going to be not more than 5 pages, including references and also some photos that you can use to support your idea. Okay, so do you have any question for your first homework? No question, class?
No question. Everything's clear.
Huh? Yes?
No question. Everything's clear.
All right, so you can keep this one, and we are going to have a 10-minute break. After 10-minute break, we are going to continue our lecture on the other chapter, on the other part, okay? All right, class, so I'll see you back 11:40. Okay, kick.
The 5 pages of the homework, including for the front page of the homework.
No, the front page is different, but what I want to say is that all your discussion and all your reference and everything has to be included within the 5 pages. It can be less than that, but not more than 5 pages.
Yeah, thank you, Doctor.
All right. Continue a bit more on still on the introduction part of the design, on the effect of wind on the structural design. So for this part, we are going to look into some parameters that how the wind is taken into consideration into the design of the structure. Okay. So there are types of strong winds like the extratropical cyclone, tropical cyclone and tornado, but thank God in Malaysia we are not dealing with any of this strong wind. And the wind possesses kinetic energy. And this kinetic energy is transformed into potential energy of pressure. So this is why we represent wind effect on the structure in terms of the pressure. And this pressure depends on the shape of the structure, the angle of the wind, and also the velocity and density of the air. So when you do your, for example, for earthquake, like study in the lab, you have to construct your model as the real model or the real structure that is going to be studied. For example, if your structure is the RC design, ARC structure or steel structure, you have to construct your model as it is, whatever like the rebars that you use and everything. If you scale it down, but in other words, the structure has to be representing the real structure. However, when you do your wind tunnel test, the material that you use to construct your model doesn't matter. What matters is the shape of your structure. So, for example, if you are going to study the wind effect on the bridge, RC bridge, for the wind tunnel model, you don't have to construct your bridge using reinforced concrete. It can be from wood, it can be other materials, but the most important is the shape of your structure, because that is what affect the intensity of the pressure on of the wind pressure on your structure. It is first the shape, the angle of the wind, and also the velocity and the density of the air. So all of these 3 parameters are controlled in the wind tunnel facilities in order to see how much is the pressure on the wind. And during your calculation using the code as well, the first thing that you have to determine what is the velocity that is going to be used, and this one is normally you refer to your national annex, and what is the density of the air. and also the angle of the intention of the wind, whether it is going to be blowing on the front, on the side, on the certain angle of your structure also matters, and also the shape of your structure. Static or dynamic pressure, if the air was quiet, there is no kinetic energy and there's no pressure too much. And we mentioned to you when static design or dynamic design needs to be considered in your wind analysis. So when it is like a normal state wind, it is acceptable and it is normally enough for you to go for a static analysis. However, when you're dealing with a more significant effect of wind or a wind governed structure, then you need to go for a dynamic analysis. And if you see here, this is a typical record of wind speed at 3 different heights. I mentioned to you when the one thing which is very important is that your wind profile. And this wind profile depending on the height. So if you look into here, this is the wind record and this is the time and this is the height of from the ground. So you can see here the first one is for the 40 feet and then you have the second line for the 210 feet and the top one is for the 503 feet. And you can see here it is like relatively the pattern is not too much changing, in which you have the lower ground to be like having lower velocity of the wind and it increases with the height. And what you can see here is that the mean velocity increased with height and also comparatively steady throughout the record. The fluctuation about the mean is almost the same height, and this is like when you're talking about gust, this is from one gust to another, okay? And this is the one that I mentioned, between 3 to 60 seconds, and this is the pulse. So in the when you're designing your structure, what you can see, I have already included the wind code, which are the design code for the wind inside your e-learning, and you can see I have included 2 codes. One is the European code and another one is the American code. The reason that I included the American code here, because one of the examples that we're going to see after this is using American code, and you can also have a differentiation between the parameters used in the American code and also the Euro code. However, for the examples, analysis, and the calculation, we are going to use Euro code, okay? Now, both code, you can see that they have the wind profile. And this wind profile, depending on the area your structure is going to be constructed. So we have 3 different wind profile. The first one is when you are in the city center. So when you're in the city center, you have some structures around your building and your wind profile is going to be like this one. And the second category is when you are in the suburban, where you have less vegetation and less structures around your building site, in which you have this type of profile. And if you can see, the difference between the first and the second wind profile is that the wind profile on the second one is more prolonged, is more big in terms of the values. That if you can see, for 500 feet height, for the first one, you're looking at 61, and for the second one, it is 76, right? So it is more, you have more velocity of wind, higher velocity of wind at the same height of the structure with the different wind profile. And then the third wind profile is the more extreme one, in which you are in the open area or facing the seaside. There is no obstacle for your structure when it comes to wind, and the wind profile, it is more pronounced. So you can see here, it is even more big like this, and for the same height, now you have 91 mean velocity of your wind for the same height. So the first thing that you need to decide when you wanted to design your structure for wind effect is that in which condition your construction site falls into, whether it falls into the first category, the second category, or the third category. Because for each category, you're going to use a different wind profile, and different wind profile will give you also different coefficient over here, in which it's going to affect the calculation of your wind pressure. Now, structure sensitive to gas, as we have already explained in the first, beginning part of my lecture, is of course the tall building, because tall building have higher natural period, and with higher natural period, you may fall into the resonance effect, because wind also has a higher natural period when it comes to their record. So when you are designing this kind of structure, you have to be a bit more careful in order to see the dynamic effect of this tall building, because they are one of the structure which is sensitive to gust. The second one is the radio and television towers. Also, it is a slender and tall building. Now, there's also structures that is subjected to self-excitation. Self-excitation comes from, like, not only from the wind excitation, but the structure itself vibrates more with the wind that it's imposed with. The first one is the oscillation. The most significant effect fall into this group. The oscillation is coming left and right. And then the self-excited oscillation is the alternating force that sustains the motion it's created or controlled by the self-motion. And if the motion stops, the alternating forces also will disappear. And the category which is very common is the vortex. Okay, the vortex. We also have soft flutter and also the buffeting action. So all this type of category, normally for the first one, the vortex excitation is the one that you can see through the wind tunnel, or also you can simulate your structure in the CFD. The CFD is the computational fluid dynamic software, in which with the CFD you can impose the wind blows in different angle of your structure, and from there you can see whether vortex excitation happened to your structure or not. So vortex is something like this. For example, you have a building and you have another building over here. Normally, if you impose your wind from the front like this, and then it comes like this, okay, and then it is also like this and another like this. So this one, what we call the suction at the back of your building, can also be one of can also caused by the vortex excitation. So this kind of thing, you can check on it with the CFD or also your wind tunnel test. Now, this is one of the example of the vortex, in which they have vortex over here at the back of your structure. And this is what the model that you can see using the CFD. So this is the example of the bridge that we have modeled using the CFD. And this is the wind blow over this side, and it is a little bit dark, but actually you can see the vortex excitation over here in the side. So when you have vortex excitation in here that you can see from the CFD, you can check how much is the pressure that caused by the vortex itself, right? So the vortex is, this is the velocity of the wind, and if your structure is sensitive to vortex, again you have to check on this pressure on the other part of your structures. Stop flutter is the vibration of very low frequency and large amplitude. Example, the galloping of the transmission line, and also vibration of some type of suspension bridges. So transmission line, like there is this. So you have like this one. This is the transmission line, and this, right? And sometimes this transmission line also, you have some galloping up and down, up and down, up and down. So that is also what we call the effect that you have to take care, because the more you have a galloping in here, the joint, the connection joint on this part and also on the bottom one is going to have some effect on it. The third one is the flutter. And the flutter is normally happens on the thin plates, placed horizontally in the wind that can develop violent vibrations. So it happens normally on the airplane wings. So the Aero Lab that we have in UTM also studies the effect of the flutter. So this is the one. So they constructed the model of the airplane, or like this the structure over here, and then they impose it on the wind direction in order to see how much is the vibration for the design of the wings when it is designed like this, and they can improve the design of the structure or design of the element itself. Another one for the what we call the self-excited vibration is the buffeting action. Now, the buffeting action comes from the word of buffet. Okay, I'm sure every one of you love buffet. When you go to the restaurant and then they say, okay, you can just pay like 50 ringgit and you can eat whatever you want. And in this table, you have a stack of food. Like food, and then you can just take one by one and eat and eat and eat. So this buffeting action also comes from this concept, the buffet concept. Now this happens when you have a design of a structure in the same place where the structure is like stacked one after another. And they almost have the similar height, they almost have a similar design. And the buffeting action is that when I have the wind coming from here, and this wind is going to cause a suction over at the bottom, at the back of my structure, and from here it's going to add to another suction over here and another here, and also eventually to the end of my building. Okay, so this kind of suction or vibration normally is being accumulated from one after another. So this kind of design as well, that we call the multiple tall stack in line, will cause you a buffeting action that you have to check on the self vibration or vortex excitation as well. So these are kind of things that the design that matters when you are designing for wind structure. Okay. Now, how you can check on the vortex excitation? We are talking about vortex, how you can check on it. So we said that the aerodynamic flow around obstacle depends on 3 parameters. So one is the velocity, the density, and the viscosity. So if you combine these parameters, it can give you one dimensionless parameter, what we call the Reynolds number. So what is the Reynolds number? Is actually density times the velocity, and this is the diameter, divided with the viscosity. So what this Reynolds number can give you is that if you design and then you check the Reynolds number is greater than 50, so it gives you the possibility of vortex excitation on that structure itself. Okay, so you can use this one as like a rough estimation in order for you to check whether your structure is sensitive to vortex or not using the Reynolds number. Now for this Reynolds number, they also have done many experiments for different shape of your structure, like circle, square, rectangular, and they have come into a different coefficient as well. In order to calculate for your frequency of vortex excitation, for example, if you take a cylinder shape of structure and you have this frequency is equal to 0.86 times the velocity divided by 4.3 times the diameter. And if I simplify this, I will have it is equal to this one, and I can represent it as a Strouhal number. Strouhal number is the frequency times diameter divided by velocity, is equal to 0.2. So what the given by your code is the Strouhal number over here, in which this Strouhal number also you can use in order to calculate for your vortex shading or your critical velocity. We will see in after this for the calculation. So the force caused by vortex you can calculate using this equation, okay, in which the Ck is the coefficient for wind equal to 1.0, and then the rho is the density of the air equal to this one, and then this is the velocity, this is the area, and this is the frequency of the vortex shading. So the harmonic Strouhal number, also the one, the S that I mentioned to you, you can use it in order to get what is your critical velocity. So what this critical velocity is saying to you is that if you get what is the critical velocity of your structure, in which you can calculate using the frequency times diameter over the Strouhal number. Strouhal number is the one you can get it from here, okay? For example, the cylinder you have 0.2. And the diameter and also the frequency you can calculate it. So once you calculate the critical velocity of your structure, you can check it with the side. If the critical velocity is almost fall into the anticipated velocity on the side, then it is also sensitive to vortex. So these are also the kind of indication that you can use in order to see whether that structure is sensitive to vortex or not using the critical velocity, okay? Now, if I, for example, calculated, for example, I have a building, okay? Now, with this building or like a tower or something, and then I calculated, I get my V critical velocity to be say 25 meter per second, okay? And I'm going to construct it in Skudai. In Skudai, I check on Malaysian National Annex, the velocity basic wind speed is 30 meter per second. Now, do you think this structure is going to be safe or not safe when it comes to vortex excitation? Think about your answer first. We'll call for someone to give the idea. We'll call for Tae Junxiang. Where are you, Tae? Yes. Tae, can you understand the question?
Sorry, can you repeat again the question?
Okay, so I mentioned, my question is that if I have a structure or like a tower or something like this, that after calculating the critical velocity, I found out the critical velocity of my structure is 25 meter per second. And I wanted to construct it in Skudai, in which when I check on Malaysia National Annex, the velocity, the basic wind speed in Skudai is 30 meter per second. My question is that, is this structure safe in terms of vortex excitation, or it has a risk of vortex excitation?
Oh, so I think it is safe.
Safe.
Yes,
Why do you say it is safe?
because it is under the Malaysia National Annex.
But this is like, what it says, what do you understand about V critical velocity?
Very critical, I think is what the most critical building that can withstand.
The critical velocity that this building can withstand.
Yes.
Yes. So if the building can withstand 25 meter per second, and on the side it is 30 meter per second, is it safe?
Oh, sorry, I listened wrongly.
Mm-hmm.
So I think it's not safe.
It's not
Because
safe, right?
building only can withstand 25.
And on your side, the wind can go up to 30, right?
Yeah, so it's not safe.
All right. So when it is not safe, what we can do in order to make it safe? I'll call for your other friends. Thank you,
Okay.
Tay, for your opinion. Have I called for ZZ live today? ZZ, where are you?
Yes. Yes, doctor.
Okay, so what do you think, ZZ? How we can make this building safer?
Maybe do some changes on the materials.
Changes on the materials. What materials?
Building materials for the strength.
What do you mean with the building materials? You mean we change from RC concrete to RC steel? F2 steel?
Yes.
But what if the client wants to have RC building? Can you just simply change it to steel?
No.
No? Okay. So other approach, other suggestion?
Change on the design.
Change on the design, on the structure design. What is your aim in changing for your changing in structure design? What do you aim to have?
To increase the to increase the building's ability to resist the wind.
All right. So thank you, Zizi, for your opinion. Right. From our friend's opinion just now, he mentioned that if in my calculation, my V critical is 25, meaning the critical velocity that this structure is imposed to is 25 meters per second. And then on the side, it may go to 30 meters per second. Definitely this structure is going to be sensitive to vortex, meaning I have like not a safe feeling as a structure engineer that one day this building may be imposed with 30 meters per second, then it can fall into the vortex excitation, right? So what I can do, like your friend Zizi said, we can increase the critical velocity, meaning we can increase this one in such a way that it can resist this 30 meters per second. So how we can increase it? Maybe I said, okay, let it increase to 35 meters per second. Because if the critical velocity is 35 and on site is only can reach to 30 meters per second, so I'm safe. It cannot reach to my critical velocity, right? Now, how the next question is how you can increase it, what you can do. So you check on this equation, because this is the equation of critical velocity. Critical velocity, it says that frequency times diameter divided by Strouhal number. Now, if your structure is a cylindrical, Strouhal number is already fixed, 0.2. And your diameter, if, for example, I want to construct a structure in a place which is already fixed, the border of my structure construction site is already fixed by my client. I can only construct my area of this one. So this is the size. Can I change the size? No, I can't, because this is the boundary that I have. Maybe they say, okay, this is the maximum you can go. So can I change D? No, I can't. What I can change else? I can check on the last one. The last parameter is the frequency. So how I can change the frequency of my structure? What I can do, if I want to increase my critical velocity, I need to increase this frequency, right? Because frequency increase, V criticals increase. So how I can increase the frequency? I can increase my stiffness, because frequency is in the proportion to my stiffness. Now, the next question I can ask myself, how I can increase the stiffness of my structure. So if I have a structure like this, I want to make it stiff. It's very easy. Now you can think of how you can increase the stiffness of your structure. You can either put bracing, already stiffer, or you can increase the column size, already stiffer, right? So all this kind of thing you can play around in order to increase the stiffness And eventually, when you increase the stiffness, you can increase the frequency. And when you increase the frequency, you can increase the critical velocity. So these are kind of things that as engineer, you can propose to your design and see what is the effect on when it comes to the wind forces on your structure, right? So this are the things that I mentioned to you. You can add braces. You can also for the building, you can add braces. Also for these bridges, you can add more cables in order to make it more stiffer. Other than that, you can also add, as I mentioned to you before, you can increase the damping, right, by adding mechanical devices. So we mentioned just now, when you have more damping, the amplification factor is going to be lower, and with lower amplification factor, eventually you may reach to a static response of your structure. So these are the things that you can increase, like with a tune mass damper, with the liquid damper, or with the viscoelastic damper. All type of dampers you can add in order to increase your damping. Or you can also use vortex suppressing devices like this one, like these tracks and everything, in which in your assignment you can check more on the example of how you can reduce the vortex excitation, or you can increase the damping of your structure. So I leave it to you in order for you to explore more on this subject. These are all the kind of introduction that we can use for our discussion on wind effect on the structure. And of course, if you wanted to check more on the case of vortex, you can check on the failure of the Tacoma Bridge, how it happens, and perhaps if it is today, how you can reduce the effect and save your design for this kind of structure. Okay, so that is the second part of my lecture. It's just again some an idea of what is the critical velocity, what you can check on when you wanted to see if the structure is sensitive to wind or not. So these are the parameters that you can look for and that you can play around on the parameters in order to reduce the wind effect. Now, on the third one, what I'm going to share with you is more on the, hold on a second. Okay, so the third part is going to be more on the design. Have you checked the code that I share with you in your e-learning, or you haven't opened it? Belum buka lagi? Right, can I show this one? I'm trying to share my slide. I'm not sure whether you can see it or not. Can you see any presentation slide?
No, I cannot
Not
see
yet.
it.
Not yet. You haven't seen it. All right, so I'll try one more time. Can you see it now?
Yes.
Okay, so thank you for verifying it. Now, in this part of the lecture, we are going to, I'm not going to be too much explaining it too much taking time. What I'm going to share with you is that we are going to look more into the design right now and the parameters that you're going to include in your wind analysis, and how these parameters are taken into the code, and why it is important for you to look into these parameters. Okay, for this part of my lecture, we are going to also check what is the effect if you do your analysis, a static analysis for a structure which is sensitive to dynamic response. I mentioned to you before, if you have a high-rise building or slender structure, which is like the response may have dynamic response to wind, you shouldn't use static design, because static design will not be too much safe for you, right? So if you wanted to see this in real calculation and real example, you can check more in our textbook, that is the Dynamic of Structure by Anil Chopra. So I'm going to also explain this in my example, how for a structure which is slender structure and you design it for static, it is not safe. And we can just go through slightly in order to show what is the difference between static design and dynamic design for this kind of structure, okay? And how you can decide to analyze it and what are the procedure that you have to think about. So for this one, since I take the example from the textbook, and this textbook is using American code, so we are also going to look into the American code that I uploaded into your e-learning page. Okay, for the design calculation and analysis, we are going to use the Eurocode. So for this one, when we're talking about wind loading in design practice, as I mentioned to you, most buildings have wind pressure with little dynamic effect. So basically, you can design it like easily with static design. You can use the static design for your analysis. And for the static design, it starts with the stagnation pressure, QS. And using the fluid dynamic, what we knew is that P plus 1/2 rho velocity square is equal to constant. And P is pressure of air, rho is the density of the air, in which if you use the pound per second square feet, it is like this one, and V is the velocity, okay, and they are constant. Now, if I have a structure which is like this thing, okay, and I have wind pressure, wind velocity imposed to my structure, and it is going to be like this, okay. So if I look from the top, okay, look from the top, it is going to be look like this. This is my building, okay. I look from the top in here, and this is my velocity, and this is my wind flow, and this is the backward. So in wind, you are going to use two terms. One is windward and another one is leeward. It is very important first to understand what is the direction of your wind blows. So from here, for this example, the wind comes from this direction. So the area which is in front of my building is called windward. The area behind the direction of my building is called leeward. Okay, so windward, leeward. There are two terms that you need to remember. Now, when I calculated it, for example, in here, for this V, for the area in front, I said this is area number 1. And on this area that is on the surface of my structure, I say area number 2. And behind my structure is area number 3. So if I consider the wind which is on the area over here, definitely the same wind that is coming from this direction is coming into the surface of my structure, right? So in other words, so if I put it in here, I would say that for area, for the wind pressure, for wind velocity in 1 is equal to, for the wind in this surface, number 2, because it is in the front. So 1 equal to 2. If I have P plus 1/2 rho V, and this is for area number 1, 1 and 1, like this one, P1 plus 1/2 rho 1 V1 square will be equal to P2 plus 1 over 2 rho 2 v2 square. So since this is the surface of my structure in which the wind will stop, because there is no movement of wind over here, velocity equal to 0, so I cancel it to 0. Now, if I just put it to the area over here, I take P1 over there, it's going to be P2 minus P1 equal to 1 over 2 rho V2 square. So since this is always going to be equal to more than 0, so it is always giving me positive value, because this one is always positive. Whatever it is positive. So the difference in the wind pressure in front over here, it is always positive. How about the difference between 1 and 3? Okay, so whatever wind blows, that in the air, the front will eventually come to the back. Okay, so that's why I make 1 equal to 3. So again, if I put the equation P1 plus whatever it is in P1 area equal to P3, 1 over 2 rho 3 V3 square, and if I make it P1 minus P3 will be equal to 1 over 2 rho 3 V3 square divided with this one. And if I make it simplified, I will have 1 over 2 rho V3 square minus V1 square. So you can see here the velocity of wind on area number 1 will be always higher than area number 3, right? Because in area number 3, the wind velocity has already reduced by this structure over here. So in other words, the V3 is smaller than V1. And if I minus this, it's going to be negative, because V3 is smaller than V1. So the differences is going to be less than 0 or negative. So when you calculate your wind pressure, you will have positive or you can have negative. So don't get confused why my calculation is negative, because negative means suction and positive means pressure. So in other words, if I, for example, calculated for my structure, okay, and I have in here positive, say positive something, in here negative something, and in here positive, in here negative. So meaning in the front area over here, I have pressure. And on the back side, I have suction. And in here also I have suction, and in here I have pressure. Either you show the notation with plus or minus, or with arrow. Arrow pointing into the structure is pressure, and arrow going out from the structure is suction. So there are two values when it comes to design, or whether it's pressure or suction. Okay. So in our design, first we decide first what is your QS, stagnation pressure. In which stagnation pressure, it depends on your velocity. Remember I mentioned to you that you need to check on your national annex for your velocity, your basic wind speed. So this is the one that you're going to decide first. Density, it is very common. We use 1.5 for the normal area. Or if you have a more specific site condition, then you need to check what is the density of the air on that area. Then velocity is the one that you can get from your national annex. So you decide what is your the stagnation pressure, and from this stagnation pressure, you're going to introduce more coefficient in order to get what is the final pressure of your wind pressure. So there are parameters that you need to take into account. As I mentioned to you, when it comes to wind design, there are many more parameters that is taken into account. And the first one is the CQ, pressure coefficient. Okay. What the pressure coefficient give you is describe the wind flow pattern on building depends on the building shape and surface condition. So where it is going to be taken care of, CQ page 5 of your code. Okay, we will go into your code later after we come to this one. So if you can see, the CQ depends on the building dimension, okay, in which It is also depending on the ratio of L over B or H over B. And this one is has been obtained from numbers of wind tunnel experiments. So in here, what they give you in the code is this is the CQ. Okay, this is the area for the CQ, and this is the L2 over B. So this is your building. This is the length, and this is the height, and this is the B. Okay, the B is the dimension which is facing to the wind blow. Okay, the cross section, the crosswind dimension. That is the B, and this is the H over B. What is given to you is that if I have H and I have B, okay, CQ, as you can see here, CQ increase as H over B increase. So this is the ratio. If I have H over B 2.5, my CQ for L2 over B, okay, if I take the ratio L2 over B equal to 1, meaning it is a rectangle block, completely a square, sorry, square. L and B is the same. So if I have a square, H over B, as H over B increase, my CQ also increase. So what does it mean? If I have a slender building, okay, for example, if I have a building like this, or if I have a slender one, definitely my H over B is going to be increased, right? Because B is smaller than this one. So if I have a slender building, it says my CQ is going to be increase, increase, and increase. And between 5 to 10 is going to increase significantly, right? So that is what the CQ first gives to you. The second one, it says for a square shape like L over B equal to 1, it's going to give me the peak value of my CQ. Now, what is the significance of this CQ? Since we have P equal to stagnation pressure times CQ, meaning if you have higher CQ, you have higher pressure. That's what is significant. And as I mentioned to you, after H over B 5, the increase is more significant. So you have to be more careful when you have H over B more than 5, right? Because it says, since the changes are more rapid, dynamic effect might be significant. So when you check your structure, when they are very slender, you have to also check on the dynamic effect. So this is only the one that I check with you. And the other one is the effect of discontinuity and surface on CQ. Also, the code gives you effect of discontinuity. What it means is that if you are on the roof corner, it says that the CQ is going to be higher. I'm sure that you have been in the rooftop restaurant, right? For example, you have a building and you have a rooftop. And this is like some kind of a small gate for you not to fall. Okay. I think in Kuala Lumpur you have a lot. In JB you have like in this on top of the hotel area building you have this. So people like to sit on the corner over here compared to in the middle here, right? Because in the corner you can look front and you can enjoy the view. Or you can say, all right, I'll sit on this one. I don't want to be sitting in here. And if you realize, the moment you go into the corner over here, you have more wind compared to your table this side. If, for example, your wind blows from this one, okay? So if you are sitting here, you have more wind compared to this one. Why? Because it says that if you are in the area of discontinuity, on the area of like the edge, for in other words, you have more wind pressure compared to this area. So this area will have more wind pressure compared to this one. This is what it means. So in the code, you will decide which area is this one. So you will have different wind pressure on this and different wind pressure on this one. That's what it says. And this coefficient also will be taken into consideration on your CQ. In Eurocode, you have different parameters. In American code, also different parameters. But the same concept is to check how much is the pressure on different area of your structure. So this is the one that it says, if I check on this curve, if I am at the corner, okay, I'm at here, B equal to 0, meaning I'm at the corner of the corner. So my CQ is 4. And the more I go in, my B is bigger and bigger. For example, I got here, then my CQ is 1.2, for example. So these are the things that being like considered in your design by taking into consideration the effect on the CQ. Okay, where you're going to check on this one? In here, table 16H, we are going to check on it. This one. And the third one is the effect of building height on your structure. So just now we have P equal to QS, that is the stagnation pressure, in which stagnation pressure depends on the density and the velocity. Now you introduce the CQ just now, right? You introduce the CQ. And another one that you need to introduce is that effect of the building height, CE. Remember I mentioned to you, you need to check on your site, which is the site in the city center or less vegetation or open area for this one. So this is the wind profile that you're going to check. And how they are going to get the coefficient here from CE. From where you can get the CE is page 4 of your code that I give to you. You can flip if you have the code right now. And this is also the CE that you're going to introduce. The other one is the effect of opening, what they call the permeability, because like the more opening you have in your structure, it will have different impact on the pressure or the suction on the building itself. So if I get the ratio of the opening to the total area of my building and I plot it, what I can get is this graph. Okay, so this one, the straight line is when there is no opening. The dot 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 is when there is opening. So you can see here, in terms of pressure, there is not much difference. But in terms of suction, for a structure with more opening, the suction is less. The pressure is more than that. But in the front area where the pressure, you have more changes. But in terms of the suction, in terms of the pressure, you don't have too much changes. But in terms of the suction, yes, you have more significant change between building with opening or not opening. Now, the code, the simplified equation that the code has given to you is this one. If you want to get the pressure, the wind pressure equal to coefficient from the height times the coefficient from the shape, from the other part of your structure, times the stagnation pressure that comes from the velocity. And also you have a new one here, importance factor. Importance factor comes from the how important is your structure when it comes to your design, whether importance factor is 1.0 or 1.25. I'm sure you have already seen this importance factor when you design your structure for earthquake, right? There are structures like fire station, police station, hospital, which is very important, and you need it to be functionable even after disaster. So your importance factor will be 1.25, meaning whatever calculation you get here, you're going to increase it 25%. And for standard building, the factor is 1.0, meaning whatever calculation you have, you're just going to take it as it is. That's what it's called, the importance factor. And you can check it on page 6 of your code. So this is the one I simplified for you, CE. You can get it from table 16G. If you have your code right now, you can flip it. 16G, CQ, 16H, and QS, 16F, and IW, 16K. So you get all these equations, and you will have your pressure, for your wind pressure based on American code, okay? And this is the coefficient. But however, it has also limitation. It may seem to be very simplified, very straightforward and simple. However, it says that the limitation, if your H over B is more than 5, okay? You are not to use this one because you remember just now H over B is 5 here, and then after that H over B 10 is already here. So it is too much difference, and because of these rapid changes, they said that it may be due to the dynamic sensitivity of your structure. So it is not too much safe for you to use the coefficient that is given by the code. The second one is sensitive to vortex. Definitely, if it is sensitive to vortex, then you should be very careful. How you can check the sensitive to vortex? One is the V critical, and also the beta ratio that you have just now, or building over 400 feet, because the CE factors that you have this wind velocity, wind profile, it's given to you up to 400 feet. Above than that, they are not too much safe for you anymore to use it, okay? So you need to go for wind tunnel or more reliable method in order to check on them. If I can give you a bit checking on your code, okay? So this is, I share with you. Okay. All right, so can you see now the Adobe? The sharing from the PDF?
Yes.
Right, so in this PDF that I open right now is the American code, okay, Uniform Building Code. So this is based on American design. As I mentioned to you, I extracted this because our example is using this one, and it is more simplified for you to check on it. So this is the equation. The design wind pressure, as you can see here, P equal to C is CQ, QS, and IW. And from where you can get this coefficient that I mentioned to you, the table 16G, the first one is this one, table 16F, the stagnation pressure, the QS, then that is depending on the basic wind speed. So basic wind speed, you can either take it from this table or you can calculate. And after that, you also have CE, the gust coefficient based on the height, that is from table 16G. And this is based on your type of exposure, either your exposure D, which is the extreme one, the one facing to the sea, exposure C, which is less vegetation, less building, or exposure B, which is in the city center. So you can choose first which type of exposure and how much is their feet. So you can see here, the maximum given for it to you is 400 feet. So that is why the code said above 400 feet. If you want to use it, you can, but there is no guarantee of your safety, okay? And this is the table 16H, the pressure coefficient. So you can check what is the structural part that you're going to design. And for example, if you are designing frame or system, whether it is windward wall or leeward wall, and this is the coefficient that you're going to use. Like for just now I said, windward wall is 0.8 inward. Leeward wall is 0.5 outward, so meaning this is positive, and the other one is going outward, so meaning it is negative, meaning it is suction, okay? So these are the parameters that you can get. And another one is what we call the importance factor, table 16K. So this is the importance factor, that is the mean importance factor that you can use for essential facilities, hazardous facilities, or special occupancy or standard occupancy. And this one is giving you differences between the additional safety factor that you can add to your design calculation or what, right? So this is the the code that you are going to see if you are using American code. Of course, it has been again improvised time to time in order to make it more detailed for you, and similar with the Eurocode as well. Okay, so for this one we are going to see one example which is very simplified, and also to just see the difference between if you use this code. It looks very straightforward, right? It looks very simple, and whether it is safe or not for a structure which is very slender and when dynamic response is governing or not. So a very short example I will share with you in here. So for that code, you can flip when you are at home, and dynamic win. Okay, so this is the example. If you wanted to check more on this example, you can refer to the textbook by Anil Chopra, Dynamic of Structure. So for this version, it was in page 316. What this example is given to us is that it wants to show the dynamic response of RC chimney to vortex excitation due to wind. So when you have your design and you wanted to start your design analysis and you wanted to know whether, okay, can I go for static or should I go for dynamic? This procedure, I have selected this example because it shows you how you can first decide on it, right? You can, of course, it's going to be a different scenario in your workload, in your work area, but you can at least have some guidance on how to start your design. So the parameters or dimension of the structure is given in here. It was 600 feet height. So the given limit of the code is 400 feet, right? And right now you have 600 feet. Of course, it is beyond what the code has given to you. And the diameter is 50 diameter and the thickness is 2.5 feet. The damping ratio is 5%, the EI is given to you, mass also is given to you. Now it mentioned the wind velocity is given to you is 100 miles per hour at the probability of 0.02%. Annually, and the site is flat and open. However, you have also a steady wind speed of 50 miles per hour. That is what you have for this example. And it asks you whether the structure is sensitive to vortex. And it also needs you to calculate the base shear and the moment due to self-excitation that is coming from vortex. And after that, it needs you to also calculate how much is the base shear and the moment when you use the code, okay? And you can compare it, whether it is lower or whether it is higher, or in other words, whether it is underestimate the real calculation or not. So in order to answer the first one, is it sensitive to vortex or not, what you can do, you can check the beta ratio. If beta ratio is close to 1, then you can say that it may be sensitive to vortex, or you can also check on the V critical. If V critical is close to the V velocity on the side, it may sensitive to vortex. So how you can check the beta factor is using the natural period of the structure and the natural period of the excitation in here. Then you can compare it. Okay, and the determination of base shear and moment from the vortex, you can use your dynamic analysis that you have already learned with Dr. Wafai. I'm not going to go into detail because I'm sure you have already covered this topic in detail with him. And then for this number 3, for the pressure, for the things you can check with the equation P equal to C E dot CQ dot QS dot IW. And when you get the pressure, you can change it into the force, and then you can check how much is the base shear and how much is the moment, and you can also compare with this one. So basically, in general, that is the all procedure. So what I can say is that the first one, to check the beta factor, you can first check on the structure part, get the frequency, angular frequency, and natural period, and the excitation also. This is from the wind or the vortex. You can get the same frequency, angular frequency, and the natural period. Then you get the beta factor. All right, so for this one, for the frequency of the vortex, because we need the frequency of the vortex as well, you can use this equation, okay, with the Strouhal number 0.2, because it is a cylinder. Now, from the also you can check the vortex force using this equation that we have already checked just now, and also the V critical from this one, and you can compare it, right? For this one, I will just go in brief on the calculation part. This is the excitation that comes from it, the force that comes from the vortex, all right, the coefficient for the wind, the density, and the velocity, 50 meters per hour. And then from here, you can get how much is the frequency for the vortex, angular frequency, and also the natural period of the vortex. So you keep this value, okay? Keep this value and keep this value, because you're going to use it to compare with the one that you calculate from your structure. Now from this one, you will get your pressure, the force over area. This is the force from the coefficient just now over here, okay? And then you can get how much is the force coming from the vortex, and this is the total one. The natural frequency of the structure, this is all coming from your dynamic analysis of your structure that you have already learned before. I'm not going to go into detail. I'm just going to extract what it has. Based on the analysis, you can get how much is the natural frequency of your structure, and from here we can get this one, right? Angular frequency, natural frequency, and also natural period. Now you compare this with the one that you get from the vortex, and then you can get the ratio of 1.02. So 1.02 is very close to the beta equal to 1.0, the resonance. Then this way you can say that based on this one, it is sensitive to vortex excitation. Now also you can check on the V critical. So this is the frequency that you get from your vortex. This is the diameter of your chimney, and this is the Strouhal number. So from here I get 71.5 feet per second, and on the side I have 73.3. So it is very close to the one that is on site, meaning it has the risk of vortex excitation, because from the structure it is 71.5, and from the side 73.3. So it can fall into this category. Now, the first question is already answered, meaning we can conclude that this structure is sensitive to vortex. So the next question is that what happens if you calculate with dynamic analysis, and what happens if you calculate only with the code? So this is how you calculate using the dynamic the dynamic analysis, okay? So from the dynamic analysis, you got this equation of motion, and then you also have this dynamic amplification factor, in which this dynamic amplification factor you can calculate it with this equation. And from this equation, I can get my dynamic amplification factor to be 9.1. So meaning whatever it is that I get, I have to multiply with 9.1. That's what it means. So from here, I get my pressure due to static to be 70. So since I have a dynamic amplification factor, I have to times with 9.1, and I can get from here my base shear 1,680, and also my moment to be this one. Okay, so I keep this value. From this value, I can get how much is my base shear based on the code, considering wind velocity of 100 miles per hour. So from my code, I can get CQ for chimney to be 0.8, QS from the 100 mile per hour to be this much. Importance factor is 1 because it is a standard structure, and P, I can just say it from this one. CE I keep first because CE is based on the height. So CQ 0.8, QS this one, and IW this one. So I have P equal to 20.5 times CE pound per feet square. So if I want to have per feet length, I just need to times 50 because 50 is the diameter. Then I can get this one per feet length. So this is along the height. If I want to get the total, I can get what is the CE coefficient for 50 feet height, 100 feet height, how much is the coefficient, 200 feet height, how much is the coefficient, 400 feet height, how much is the coefficient. This is CE, okay? And then since the code did not give me for 600, I use the same, 2.34. How much, however you feel comfortable to calculate it, you can, but for this one, I make it very like elaborate in order for you to understand how I come to this value. So this one is the peak based on this one, 1.025 times CE. So this is my CE. So 1.025 times CE, I got this for 100, 200, 400, 600. And in order for me to get how much is the total base shear, I just need 2 times the height. Okay? 169, I times 50. And another 1.927, I times another 50 because this is the height 50. 2.15, I times 100 because this one. And 2.4, I times 200 because of this one. And 2.4, I times another 200 because of this. So this one. So total base shear that comes from the design is 1356. Now compare it with the one that you can calculate with the dynamic, right? So from the vortex that you calculate using dynamic calculation, you have this one, 1680, and from code, it gives you 1356. It means that it is less than what is supposed to be in the real one, and the code has underestimated the base shear that is happening due to the vortex for your structure. So this is the kind of thing that you can do in order for you to have a like initial decision on what type of analysis that you're going to use for your design. Okay. All right, class. So I think in terms of the introduction about the concept of design for wind, the parameters that is used in your design for wind analysis, and also the comparison between static design and also dynamic design analysis, I have already covered in this class. So the next class, we are going to have more hands-on calculation using Eurocode, in which I'm going to give you a sample of structure. And from this sample of building, we are going to do together in terms of the calculation using the code, how you can get the pressure and how you can impose the pressure in different part of your structure, which matters for your calculation. Okay, so that will be on the next week. Please also get ready with your Eurocode that I already share with you in your e-learning, and also your notes for you to understand it better. Before we leave, do you have any question?
Okay, doctor.
No question, yeah? All right, so if there is no question, before we leave, we are going to check on your attendance first. Okay, so give me some time. I'll check on your attendance. Hold on a second. Okay, I'm going to call first for our postgraduate students. If you're here, you can unmute yourself and say you're present, okay? Abdirrahman? Abdirrahman? No? Abu Bakar? Abu Bakar?